All right, our last speaker for today, we've already arrived at the end, but very much not least, is Theo Chawla, who has joined us this summer from Evergreen Valley College. Theo's been working with Jason this summer, and today he'll tell us about their project, Viewing Distant Worlds from Earth, Simulating Ground-Based Observations of Water in Exoplanet Atmospheres.
Thank you so much, Gwen. As Gwen mentioned, I'm going to be talking about simulating ground-based observations for a new near-infrared spectrograph that Nee actually introduced really well for us today, that near-infrared spectrograph, Henrietta. But first, I want to talk about why exoplanet atmospheres are interesting to us. So as many of us know, exoplanet research is a field that has really expanded in the last couple decades. We went from only being able to observe planets within our solar system to understanding that most stars have planets around them, and to being able to identify thousands of planets outside of our solar system. A popular way of beginning to investigate these exoplanets are taking mass and radius measurements of them using the transit and radial velocity methods. But mass and radius can actually be deceiving. So we have a great example of this in our own solar system, actually. We have Earth and Venus that have very similar mass and radii, but completely different surface conditions because of their atmospheres. And so because of this, atmospheres really contain this wealth of information. They can tell us about formation history, physical processes in exoplanets, temperature, and so they're definitely of interest to study when we think about characterizing exoplanets generally. To observe them, in this project, we're focusing on the transit method. So we are observing light from a parent star as it passes through an exoplanet atmosphere and looking at the specific wavelengths that atmosphere absorbs to get an idea of the composition of that atmosphere. I also wanted to point out just what an exoplanet transit might look like. So we have a significant dip in flux as that planet passes in front of its parent star. And by looking at transit depth at different wavelengths, we can get an idea of what light is being absorbed from that exoplanet atmosphere. These observations have been made from space-based telescopes, specifically and most popularly with JWST. And these observations are really fascinating. They contain a wealth of information, but space-based observations do have some limitations. Specifically with James Webb, it is really difficult to get telescope time on that instrument. James Webb is observing a wide variety of targets and not just exoplanets. So it makes it difficult to observe a large number of exoplanet atmospheres. So this opens up the option of maybe investigating ground-based observations of exoplanet atmospheres. And this has a couple of advantages. It's significantly more cost-effective. We have more access to observation time, maybe being able to observe night to night. We have access to instrumentation and telescopes on Earth and the potential to build more instrumentation if we need it. And we can observe more targets in total. Ground-based observations could also potentially inform space-based observations in the future. And this is where Henrietta comes in. It is a new near-infrared spectrograph whose goal is specifically to characterize exo-atmospheres from ground-based telescopes. As Nee mentioned, it is a high spectrophotometric precision, low resolution instrument with a resolving power of about 200. It covers a really wide wavelength range from 0.6 to 2.4 microns. And it's being designed for the 1 meter scope telescope at Las Campanas Observatory. And so one of the elements, or one of the molecules that we're really interested in particular in exoplanet atmospheres, is water, both in terms of planet formation history, but also in terms of temperature regulation and potential habitability as well. It is complicated to observe water from ground-based telescopes, though, because our own atmosphere contains so much of it. And so we can see this effect in a transmission spectrum of Earth's atmosphere. And so this is showing us the amount of light that is successfully passing through Earth's atmosphere from distant sources by wavelength. And in particular, we're interested in these 4 water absorption wavelengths. And we can see that water has a really significant impact on Earth's transmission spectrum in the near infrared range that Henrietta will be observing in. This transmission also changes as water content changes. So here I'm going to overlay what it looks like, the transmission spectrum at a much higher water content. And we can see that in one of these deep water bands, transmission might change from 80% all the way down to 20% as water vapor increases. And so you can imagine if we're taking observations in these water absorption wavelengths, changes in Earth's water vapor is really going to impact the flux that we're receiving at these wavelengths. This is made more complicated by the fact that Earth's precipitable water vapor is constantly changing because of Earth's water cycle. It's changing on a scale of hours and in a way that can actually mimic exoplanet transits. And so to mitigate this water vapor noise, Henrietta intends to use a technique called differential spectroscopy. So it's going to use a wide field of view of a maximum of 25 arc minutes to simultaneously observe a target star and a reference star and take spectra of both of those. The target star will experience this dip in flux from the exoplanet transit, while we expect the flux of the reference star to remain constant over that period. But they will both experience similar effects of Earth's precipitable water vapor. So our hope is by dividing these two signals, we can remove that common noise effect and better recover the exoplanet transit. And so to begin simulating this effect for Henrietta's observations, we start with a high-resolution stellar spectrum and multiply this by Earth's transmission spectrum at different water contents. And from this, we receive a model of how flux is going to change based on wavelength and by water content. The other significant noise source that we're simulating is photon noise, which is dependent on the photon count that's received. So this can be related to several things, including resolution, exposure time, mirror size. Here I'm simulating the effect due to stellar magnitude. And so one of the ways that Henrietta intends to mitigate this photon noise is by observing at a low resolution. So here, our next step in simulating these observations is to bin down our high resolution spectrum to the resolution that Henrietta will be observing at. And so you can see that we lose these granular effects of the high resolution stellar spectrum, but we do increase the number of photons that we receive per wavelength bin, which will help mitigate that photon noise. One of the effects of reducing that resolution, though, is that because we lose some of these granular effects in the stellar spectrum, it becomes more difficult to remove water vapor noise. So we can see here, even I'm simulating here a target and a reference star that have exactly the same effect of precipitable water vapor. And we can see even if we're dividing exactly the same signal at a resolution of 200, we're still not able to completely remove that noise. And this effect is greatly reduced when we use higher resolutions. And so now we can take a look at in what cases differential spectroscopy can be effective for these kinds of observations. So here I'm simulating a light curve of a target star that does have an exoplanet transit, but initially it's not visible at all. All we see is the precipitable water vapor noise. This is the light curve of a target star, and you can see that it experiences similar amounts of this noise. So when we divide these two signals, we're actually able to recover this exoplanet transit in a way that would not have been visible initially from that target light curve. And this is under specific conditions. So using a low angular separation, very similar spectral type, and for very bright target and reference stars. So our next questions end up being, under what conditions can we successfully use this method? And the two parameters that we primarily looked at were wavelength and spectral type. So talk about wavelength first. We can see here I'm simulating a divided signal. So applying this differential spectroscopy effect for a light curve at 0.93 microns and then again at 1.9 microns. And we can see that the transit is much more visible at 0.93 microns than it is at 1.9. And we can actually trace this back to the depth of the water bands that we see in Earth's atmosphere. So that 0.93 micron transit is in this wavelength range right here. And we can see that this band is much shallower than this deeper band here. where we see that 1.9 micron transit. And so we can see that these these deeper water bands might be significantly more difficult to observe in because we're less able to remove that effect because Earth's water vapor will affect observations more strongly. We were also able to simulate our data based on spectral type. So here we are looking at a target star of 4,000 Kelvin, and we're assuming main sequence stars for all of these, and a reference star of 3,000 Kelvin, so relatively similar in spectral type. And here is what our transmission spectrum looks like for a reference star of 8,000 Kelvin. And we can see that the difference between the spectral types is not primary. And what we see primarily is that we are unable to remove a lot of this noise, especially from these deep water bands, from our signal. So we are vastly over predicting the amount of water vapor in comparison to our reference exoplanet transit. And initially, this seems pretty discouraging. It seems like maybe this differential spectroscopy method is maybe not efficient under these conditions. But here we are simulating this at an angular separation of, on the larger end of Henrietta's capabilities at 15 arc minutes. And one of the things that we're exploring is that angular separation also has this large impact on how recoverable that exoplanet transit is. So we can see at the maximum angular separation of 25 arc minutes, the transit is much less recoverable than at 5 arc minutes. And also, the relationship between water vapor or how water vapor changes based on angular separation, this relationship is not really well understood. So in our simulations, we're using kind of a worst case scenario that is based on a study done on the transparency of the atmosphere as a function of angular distance. But this study doesn't actually take into account precipitable water vapor specifically. It is just looking at the effect of the atmosphere. And so in other studies, for example, this paper by Ting Li in 2014 finds that they found that precipitable water vapor did not change significantly, even as angular separation increased significantly, even to a change of up to 90 degrees. And so some of our next steps will be to better understand this effect of angular separation. And so if we are operating more on our best case scenario of how precipitable water vapor changes as a function of angular separation, it's possible that Henrietta will be much more capable of successfully recovering transits than our simulations predict. We also will be simulating different types of exoplanets and exposure times. And in particular, we are interested in analyzing what this might look like for different instruments. Henrietta is kind of a precursor for future instruments, and in particular MIRMOS, which Tanya talked to us about today. And just as a reminder, that is it's also a near-infrared instrument, and it's a multi-object spectrograph that also intends to characterize exoplanets from ground-based telescopes. And so it has a much more moderate resolution and a much larger mirror size. So we're interested to see how effective this method is with a different instrument as well. And so some of the key takeaways that I want to leave you with today are the large impact that Earth's precipitable water vapor has when we observe at these water absorption wavelengths. And the potential effectiveness of differential spectroscopy to remove that water vapor noise, and how this might unlock the future for potential ground-based observations of exoplanet atmospheres, specifically in terms of characterizing water in exoplanet atmospheres. Thank you so much.
This might be a question out of left field, but I'm thinking about climate change, and does that have an impact on the water vapor in the atmosphere? And do we understand at all how that impacts it? And is this a way we could study that?
Oh, that's a really interesting thought. Yeah, so I haven't looked at all at how climate change has been changing precipitable water vapor in my observations at all. But I think one of my hopes for Henrietta is that we will get a better idea of how specifically precipitable water vapor changes by angular separation. I don't know if it would be able to be used to study effects of climate change as well. There are other studies that look at how precipitable water vapor changes over time, so that's pretty well studied. Yeah, that's a really interesting question. I think that'll be something worth looking into for sure, especially for future observations.
I was wondering, how many targets do you have available that have a bright enough star within 5 arc minutes?
Yeah, definitely. That was one of my questions when I first started the project too. Based on, I'm working with Jason Williams, and based on his initial survey of targets in the southern hemisphere, he based his the field of view on Henrietta to capture target stars that would be or reference stars that would be good complements to their target stars for the 10 brightest exoplanet objects within the southern hemisphere. So at least starting out, like, we have a good sample of targets to look at. Also, I mean, this is just like personal observation. I was poking around at the Simbad field of view for some of the exoplanets that we were simulating. And at least for we were simulating 3 different types of exoplanets in this project, although I didn't really get to show much of that in this presentation. And at least for those ones, I was very easily able to find reference stars within 25 arc minutes that were of similar spectral type and a similar brightness to the target star.
Okay, thank you.
And we'll get the last question to me.
Thank you. That was a fantastic talk. I just have one naive question, and which is, so I don't know much about like the vertical profile of like Earth's water vapor. So how much it changes according to zenith angle. So is that something that you have explored, or do you like? What do you think? Like, how that will that impact the effectiveness of differential spectroscopy in this case?
Yeah, that's a great question. We actually expect that the effect of spectral type and the change in water vapor based on angular separation will be dominant over air mass effects. So it wasn't actually something that we looked at in this simulation, but it would be definitely something that would be good to add for future simulations.
All right, let's thank Theo again.